We spent some time in the last video showing that a determinant can be written using the epsilon permutation symbol. Here we have it expressed for a 3 by 3 matrix, and the way we write it out is, of course, the first number always designates the row. We have 3 rows, so you have A1, A2, A3, and then the second number, the column number, is replaced by I, J, and K. If we had more terms in the matrix, and of course we'd have more terms here, and we would have more letters underneath the permutation symbol. But we didn't prove it, but we certainly established the validity of this equation in the last video. Now, vector cross products, they can be expressed too as the determinant of matrices. So if we had vector A cross vector B, it would be written out as that determinant. Or if it was vector B cross vector A, it would be written out as this determinant. So it seems obvious, I guess, that we should expect that the vector cross product itself can be expressed in terms of the permutation symbol. And that's what we want to discuss in this video. And let's just first briefly review our right-handed orthogonal coordinate system. I'm designating these as unit vectors E1, E2, E3. And again, for the right-handed coordinate system, the way they're related is E1 cross E2 using the right-hand rule, grabbing it, the thumb points upward along E3. Or E2 cross E3, that generates E1, or E3 cross E1, we'll be doing it like, it's hard to demonstrate, like this, and again the thumb points along E2. And obviously the order is important. If we had E2 cross E1, that'd be minus E3. Or if we had E3 cross E2, that'd be minus E1. Or if we had E1 cross E3, that'd be minus E2. Well, all of these equations can be summarized using the epsilon permutation symbol like this. Here then, of course, I, J, K, I would be synonymous with E1, here would be J, E, K. But we can express it like this. Remember, in the last video, we discussed about the even permutations and the odd permutations of our epsilon symbol that designate it with a value of either +1 or -1. Any repeated indexes, of course, give it a value of 0. Now, if we use ijk's, then we would have this situation. These would be +1. The odd permutations of the I, J, and K's that have these configurations, these would be -1. So, for example, here's our general formula. EI cross EJ equals epsilon ijk. Now here, the order of the indexes matches these, I, J, K, I, J, K. What happens if we had EK cross EJ? That had to be epsilon. Of course, there's only, what would that give us? Well, there's one letter left, so that would have to be EI. It's going to be epsilon KJI. And KJI, that's -1. So this has a minus sign, and EK, that's would be E3 cross E2 would equal minus E1. And that's what we just had on the previous page. So it's consistent with that. E3 cross E2 is minus E1. So all of these equations can just simply be expressed like this. So let's see now about taking the cross product of two vectors and writing that out. So let's say we have a vector A and a vector B. And writing A in component form, be like this, say in vector B, could be like this. And again, as we explained in video 1, whenever you have repeated indexes, you're summing over that index from 1 to 3. If it goes higher, we would state so, but we're assuming it's automatically going to be summing from 1, 2, and 3. Same here. Now, of course, that means that for these repeated indexes, it doesn't matter what letter we use. We could have stated it like this, and that would still give A1 E1 plus A2 E2 plus A3 E3 and so forth. That's why for repeated indexes, sometimes they'll refer to them as dummy indexes. But let's say now we want to take the cross product of A and B. So we'll have A cross B well, that would be this, AI EI cross B sub j EJ. Now, we can collect these scalars together like this. Say it's A sub I B sub j EI cross EJ. Now, before I finish the rest of this, let's just pause here for a moment, make certain that we're comfortable with this step. Now, here we have repeated indexes, so of course that would be having A1 E1 plus A2 E2 plus A3 E3 cross this. Here then we have it like this. Again though, with the repeated indexes, but are we really convinced that this would give us the same expression as this? So let's just pause here and write it out longhand in component form. So here is vector A and vector B. We're going to take the cross product. So we have this cross this, E1 cross E1, that's 0. Then we'll have this cross this. So we have A1 times B2. Then we'd have E1 cross E2. And then we would have this with this, A1 B3 E1 cross E3. And then same thing of course for this term. We'd have A2 B1 E2 cross E1. Then we could have this, but E2 cross E2, that's 0. So the next non-zero term, A2 B3 E2 cross E3. That's that term. Then here we will have A3 B1 E3 cross E1 right here. Then we'll have A3 times B2 E3 cross E2 right here. Then with this term, E3 cross E3, that's 0. Now what happens if we have it written out like this? So we're looking at this, we see repeated indexes, some from 1 to 3. We'll do it for I first. So we'll have 1, then I is 2, then I is 3. Now we sum over the j. J goes from 1, 2, and 3. J is 1, but that's E1 cross E1, so that's 0. J is 2, so that gives us a 2 here and a 2 here. Then J is 3, so that gives us a 3 and a 3 right here. Then we move on to this term. J is 1 here and here. We have it there. J can be 2, but E2 cross E2, that's 0. It can be 3, then we'll have a 3 here and a 3 here. Then from this term, J is 1, giving us a 1 here and a 1 here. That's what we have. And it can also be 2. Right here can also be 3, but that just gives us 0. So this expression gives us these 6 terms right here, which in fact are identical to these 6 terms right here. So going back to where we left off now, this in fact is a valid step, but remember what this is. That's epsilon I j k ek. So A cross B, we can write like this, equals epsilon, this should be down here, these are subscripts, I j k ai b sub j ek. So here we have the cross product written using the epsilon permutation symbol. Now, in some textbooks you'll see it like this. Oh, notice the order of the indexes here match. That's of paramount importance. Now, we expressed in terms of component form vector A like this, but as we'll see later on, when we're using the permutation symbol, this doesn't necessarily have to be an I here. What is important is that these indexes match the ones on the permutation symbol, and after that we're just going to be, adding from 1 to 3 in each case. But sometimes you'll see it written like this, epsilon k ij. It's the same thing, but again, the order of the indexes match. We're going to stick to this notation here for all of our future videos. Now, let's just take a moment though, and I guess repeat what we did in the previous video. Here we have a repeated index for the I, the J, and the K, so let's sum over those indexes. In fact, let's just erase this for now. So here, this would be the cross product of vector x cross vector y. And again, repeated indexes, so we'll let I go from 1 to 3. So 1, 2, and 3. Now we sum over the j's. J goes from 1 to 3. But when j is 1, we have a repeated index, so that would be 0. So we start with j being 2, gives us a 2 and a 2, we have right there. Then j can be 3, giving us a 3 and a 3 right here. Now, for this term, j can be 1, giving us a 1 here and a 1 here. J can be 2, that's just going to be 0 with that repeated index. J can be equal to 3, so we'd have it here and here. Then we move on to this term. J can be 1, giving us a 1 here and a 1 here. J can be equal to 2, giving us a 2 here and a 2 here. It can be 3, but with that repeated index, that will be 0. So we have these 6 terms. Now we let k equal 1, 2, and 3 for each term. But clearly for this one, if I let k be 1, we have a repeated index. If we let k be 2, we have a repeated index. The only non-zero expression is for k to be equal to 3. And that's what we have right here. For this one, the only non-zero expression is when k equals 2. And we have that right here. For this one, the only non-zero term is when k is equal to 3, which we have right here. And for this one, k has to be 1 to get a non-zero term, which we have right here. K would have to be equal to 2, which we have right here. And k has to be 1, which we have right here. And then, remembering our permutation symbols, that's plus, this is minus, that's minus, this is plus, that's minus. So we collect the terms, and it comes out like this. Or if we had A cross B instead, then we would have it like this. And that indeed is exactly what we get if we write it out, taking the cross product of A and B, writing it out in determinate form, expand it with minors, we get this expression where these terms here match up with these terms right here. Now, of course, when we're taking the cross product, we call it the vector product because this gives another vector. So you could say, well, then A cross B, it would have component 1, component 2, component 3. Or clearly component 1 would be this, component 2 would be this expression, component 3 would be this expression. So where that leaves us is that we can have it like this then, that for the cross product, A cross B equals epsilon I j k A sub I B sub j E sub k. And I think that's where we're going to end the video. What we're going to do in the next video is consider, yes, the cross product itself is a vector, and that vector can have an I component, it can have a j component, and it can have a k component. And how would we find the I, j, and k component? Or actually, let's just continue and see if we can get this finished up in this video. So, if we say A cross B, that gives us a new vector. And if I wanted the ith component of this vector, well, that would equal that vector dotted with the unit vector EI. Or if I wanted the j component, then it would be that vector dotted with the unit vector ej. Or if I wanted the kth component, it would be that vector dotted with the unit vector ek. But that vector A cross B is what? We can write it like this. So if we want, say, the eighth component or the kth component of it, we took the cross product of two vectors, it gives us a new vector. We say, what is the kth component of that? It would be that vector that we just generated dot the unit vector ek. But that vector we just generated we can write in component form like this. So we have epsilon I j k ai bj ek. This is this dot ek. Of course, this would just equal epsilon I j k ai b sub j. Now, if we want to write just in general form, say the ith component of A cross B, then we would have epsilon. Now, this and this match here. That's because the way it is here. Our vector that we have, this index matches this index right here. So when we take this dot product here, of course that goes away, but this is still here. So this matches this. So we could write it out like this if we wanted to. Kj, but the I term has to be right here. And we have to have an A and a B, and these have to match. So this would be AK, B sub j. Or if we had, say, A cross B, and we wanted the j component. I misread this as a j. I wanted that to be an I. Let's just back up here. This, we did have it right, I'm sorry. We were okay there. This is I, this has to match I, and then these indexes have to match. Okay, now, the video is getting to be too long here, but I think we can wrap it up in a few moments before I make any more mistakes. This, if we wanted the j component, would be epsilon, and the third one here has to be j. We have A, and we have B. So if we wanted to, we could call it I, K, I, K. Now, let's just consider one of these in more detail, say this one. So we're looking here, the jth component. Now j, that usually corresponds, of course, to E2, so that would be analogous to where the j is a 2. Then that would be what? Okay, let's go back to here. This and this have to match. So we could have IK, with these indexes match, that's all that matters. Okay, now j is like the second, corresponds to the second unit vector, EJ or E2. So you can put 2 here, and we have IK, IK, so sum over these. So I equals 1, and then we have I equals 2, but then we have a repeated index, so that's 0. Then I equals 3 gives us this term. Now k goes from 1, 2, and 3. Well, when k equals 1, repeated index, k equals 2, repeated index, so the non-zero term is for k to be 3. So we have this, and here k has to be 1, everything else will generate zeros. So you'd have this, and this is a positive 1, that permutation is minus 1, so we get this expression right here. And we can find our piece of paper, our demo paper. We had that A cross B, its second component is minus this expression, so it would be A3B1 with that negative sign there, A3B1 minus A1B3, minus A1B3, just as we had then determined it previously. So hopefully this makes sense. We just kind of wanted to give a demonstration of how to express the cross product in terms of the epsilon permutation symbol. Now, what we're going to do in the next video, which will be much shorter than this one, we know that when we invert the order of the cross product, one is the negative of the other. And that's because, looking at it in determinant form, we're reversing the rows here on these determinants. When you reverse it an odd number of times, it gives you a negative sign. If you do it an even number of times, you have an odd, it gives you a positive sign. But we want to prove that this is true using the epsilon permutation symbol. And that's what we'll do in the next video.